Go. Thank you. Thanks for the reminder, and I think that's good to go. I'm just looking for the tab. My half mirror is sometimes in the way because of the housing. There we go. Okay, so YouTube is getting the live stream as well. And I think the volume is okay. I think I can bump it up just a little bit. There we go. As long as I don't cap out, the get to the red portion, I'm good. So let me bump it up even more. There we go. All right, so the first thing I want to do is to talk about JavaScript, the equivalence of the for all operator, but from the perspective of JavaScript coding. If you're not familiar with JavaScript, it's okay. Okay, this is only intended for people who already know JavaScript, so they can basically have one additional layer of understanding of the operators. So in this particular case, let me just kind of add some comments to the function. So S is basically a built-in type called a set in JavaScript, and then P is a callback function that expects only one parameter. So the idea of for all is you have to apply it to a particular set. Now, for all itself usually applied to is a universal quantifier, which means it applies to everything, but it is hardly useful, when we look at it in that context. So that's why most of the time, when we use the for all quantifier, it is applied to a particular set. It's basically so for every element in this set, blah, 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 okay? So that blah, blah, blah is done by P, which is a parameter, to for all, but P itself is a function, is a callback function. When we look at the implementation of for all, there's a result, okay? So the result is by default known as true, okay? So we initialize result to be true, and then for each element in S, okay, this E is basically an element. For each element E in the set S, what we do with result is result and P of E. In other words, result is true because of the initialization, but once it turns false, because if at least one of the PE is false, then result is locked to false. Okay, it can no longer be true again, because every single time we are only using a conjunction to combine the existing result with the result of P of E. So when this is all done, we just simply return result as a value. And that's kind of one way to look at the for all quantifier, which is also kind of interesting, because what happens when S is an empty set? When S is an empty set, the for all is going to return true. Okay, so that part is a little bit kind of awkward, but that's how it works. Okay, so when you have a set that is empty and you say for all X in that particular set, which is empty, P of X, then the quantifier itself, the entire statement, is true. So that's something that we want to keep in mind. So what we'll do today is we are moving on to the topic of Aleph Null. And Aleph Null is an interesting topic for a few reasons. Well, first of all, the symbol, okay, the symbol Aleph, which is this portion, is an Arabic character. Okay, so that's the first part that's kind of interesting. If you look at the history of which character we choose for Aleph Null. Okay, and then what we do now is we go back to the notes, and let me point out where we are at this point. So I'm hoping that most of you are at least catching up with injection, surjection, and bijection. Oh, by the way, there's a homework assignment. The homework assignment, function assignment, is released, and before you guys submit, let me warn you, this is also not a multiple submission kind of assignment. Once you submit, that's it. Okay, but you do have until September 15th, which is next Tuesday at 10:30 to turn it in. Okay, so you have plenty of time, but do not submit unless you're 100% sure that you don't want to change the answer any further. Okay, So that's one. We'll talk about the row taking thing later today, because when we talk about the Aleph Null module, we'll actually get to that part too. So we are now onto this particular module called Aleph Null, and we'll go take a look at the content. So Aleph Null is basically this is the definition of Aleph Null. I'm just going to focus on the definition here. So the definition of Aleph Null is, it really is just the cardinality of the set of all natural numbers. Okay, this funny looking n represents the set of all natural numbers. Now there are some people who say natural numbers should start with 1, and there are people who say natural numbers should start with 0. So I am taught that natural numbers should include 0. Counting numbers will start with 1. Okay, but that's just how I was taught, and that part is not even that super relevant in this case. Okay, whether it includes 0 or not is not really that important. So do we have any questions about the definition of Aleph Null? Okay, doesn't seem like there are any questions yet. All right, so when you look at the plain definition of Aleph Null, it really is just, okay, it's the cardinality of the set of all natural numbers. So now the question is, what other sets have the same or equivalent cardinality as the set of all natural numbers? So the interesting thing, which I will state first, okay, over here, is if you look at the set of all integers, it turns out to have the same cardinality as the set of all natural numbers. Okay, that really should surprise most people if they have not read this module already, because it doesn't seem to make sense, right? Because integers include negative integers, and natural numbers are non-negative integers, okay? So it doesn't seem to make sense that they would have the same cardinality. And yeah, go ahead.
Would it be infinity essentially?
Nope, it is okay, so here is the really important part is the number of elements in the set of all natural numbers is infinite. Okay, but Aleph Null is not just that it is infinity, it is a special kind of infinity. Okay, so we'll clear up that concept in just a little bit. So I want to go ahead and kind of talk about a few things about the set of integers and how it relates to the set of natural numbers. Okay, so I'm going to use this part on the whiteboard. So once again, you won't see what I'm typing. If you're interested to see how I type all of this stuff here, I can kind of move this window over here. If you find it too distracting, I can just kind of move it away from what you can see. Any preferences from the class? Because I can go either way. It doesn't really matter to me.
If you could turn on I like the live feature that you did beforehand, where you had it live while you were typing instead of waiting for it to finish.
Oh, you like that one, huh? We can change the settings to do that, I think. So let me go ahead and make some changes. Any other preferences? So Joshua is typing, so I'm gonna wait for him to, oh, okay, I have to save this first, and then go edit. Okay, keep it up. Okay, very good. This might come in handy at some point in your career, because this is using Markdown. Markdown is kind of, you can look at it as a much more human version of HTML. Now, it is not HTML, okay? But it can crank out HTML code really easily. And it's far easier to look at this than anything else. So let me change that setting. Okay, it's one of these settings down here.
Hey, Tech.
Yeah.
Is Markdown close to like YAML, or is it kind of like similar?
I don't think so. YAML is still intended for machines to read, and Markdown is intended for people to read. It's intended for very easy editing. Like if you just have a text editor, what you see in the text editor is close to what it would be, how it would be rendered. And then YAML is actually another format for machine readability, not so much intended for human.
I thought that the like the syntax of YAML was supposed to be more readable for people.
That might be the case. I have to look it up too. There we go. Okay, this is the setting here. Change that to 0, and then go back to my other document. There we go. All right, so this time it would actually refresh the HTML side in the browser as I type. Okay, I personally just kind of find that a little bit disturbing because you only see part of what I'm typing and it's not well formatted yet. But it's okay. As long as you guys understand that sometimes I'm not done typing yet, so what you see in the browser is not quite the entire finished form. All right, so let's go ahead and talk about relationship between the two sets. Okay, the set of all integers versus the set of all natural numbers. Okay, so the first thing we will take a look here is we look at the set of all natural numbers. Okay, this is it doesn't like that. It doesn't convert it into math equation format. Okay, but we can use your subset of math BB Z. Okay, it still doesn't convert it. Something is causing this not to recognize the math symbols. So maybe it has to do with the title cannot have something like that. Nope. It still doesn't do the conversion. I wonder why. Okay, so I'm just trying to diagnose the problem, and it still doesn't do that. All right, so it has to do with something that I did. And this time it doesn't even show. Okay, I broke something. There we go. So it has to do with that extra space. All right. Okay. So I can now retype the Aleph Null as a title. Okay, as a section header. That's it. All right. So the first thing we want to see is to evaluate this Boolean expression. Remember, this symbol here means proper subset of. So now the question is the set of all natural numbers a proper subset of the set of all integers? So what do you guys think? And if you have an idea, you kind of have to, at least in your mind, be able to explain it. So let's go ahead and take a look at a few members, okay, in these particular sets, okay? So the first thing I want to evaluate is this. Okay, is that true? So is it true or is it false? Come on, you guys can. 0 counts. Okay, but we are looking at a true false value here because 0 in n is a Boolean expression. It is either true or false. So Aaron is correct. It is true because 0 is in fact an element of the set of all natural numbers. Okay, which is something that I just mentioned, because when I was taught, set theory, that was the definition of the set of all natural numbers. So this is in fact true. Okay, very good. So now we look at just the next value, which is on the negative side. Okay, I need to leave an empty line here. Okay, so what about this one? Is -1 an element of n? It is false. Okay, very good. Now we take a look at this one. Okay, instead of looking at the set of all natural numbers, let's switch and look at the set of all integers. So let me go back and mention that this is false, and this one is true, right? Because -1 really is an element of the set of all integers. Okay, so based on just these few observations, okay, we can throw in one more. Okay, I'll just go ahead and throw in one more, which is just 1. Okay, so 1 is a value, 1 is an element of the set of all integers. It's true. Okay, so that's kind of goes, it's really easy to understand that one. And if I ask, is 1 an element of the set of all natural numbers, it is also true. So based on what we are seeing here, only a few examples, we can kind of see that the set of all natural numbers is a proper subset of the set of all integers is actually true. Does that make sense? This is actually true. Do we have any questions about this conclusion? Let me move the conclusion down, because it's based on the observation of the other ones. So all I did was to move n is a proper subset of z all the way to the bottom. Okay, go ahead.
I was just going to say, yeah, it makes sense.
It makes sense, right? So if one is a proper subset of the other one, can they still be considered to have the same cardinality? That really is the question. Okay, so how do we define equivalency when it comes to cardinality when we are dealing with a set that has an infinite number of elements? That becomes the question. Okay. So if you're screaming in your head and go like, "Ooh, pick me, I know the answer because I have read the module already," well, congratulations, you're ahead of the whole class and ahead of the discussion. So that's kind of what I really want the class to do, is to be able to read ahead of me, because then you kind of know what today's lecture is about, you know what the concepts are about, and you can just kind of ask questions about what you have read already, and the tricky part that you're not quite understanding, instead of encountering everything that and see everything is, oh, this is new to me, I did not know this. Okay, so that's the value of studying a little bit before class. I can also understand why it is also not so good a thing, because it's kind of like reading the synopsis of a movie before watching the movie. So if you consider taking a class as a form of, I hate to say it, entertainment, okay, then you probably don't want to read ahead of time because you want to get the surprises, right? On the other hand, if you're trying to succeed in a class and get the best grade that you can get out of a class, then reading ahead of the class when you have time is actually a very, very good idea. So I just want to kind of remind people about that. All right, so what we're going to do next, okay, without fully answering that question, what we're going to do is now we skip to this function. Okay, this is the function that we're now talking about. This function is using the set of all integers as the domain, and it maps those elements, integers, into the set of all natural numbers. Okay, so you can probably find a bunch of functions like this. Like the absolute value function is a function like this, right? Because the absolute value function, when applied to integers, will result always in non-negative integers, which, well, the other name of non-negative integers is our natural numbers. Okay, so there are quite a few functions that can exist like this, but I choose to use this particular one, not because it is really kind of ugly to look at, but because it has a very special property. So let's take a look at this function here, and I'm just looking at the text channel. If anyone does not understand what this function is about, we can talk about it. But I want you guys to spend a little bit of time first to look at it before asking me to explain it. okay? Because the best thing you can do to try to understand the material is to try to spend some time to understand it yourself first, okay? Because if I explain it, some people can just memorize, the way I explain it, which is not the same thing as understanding something. So I'll give you guys a little bit of time, and after that, if you want me to explain it, I can definitely do it, okay? And if you don't want the whole class to see that you're the one asking, you can direct message me on Discord, and I won't name any names, okay? I promise I do not name names. This is the best part of remote learning, is I can do something like this, whereas in a face-to-face class, unless you guys want to wear paper bags and masks, to a class, it's kind of difficult to hide your identity.
If x is positive, then you multiply it by 2. If it is negative, you multiply by -2 and then subtract 1.
Yep, that's exactly what the code is doing. So Aaron is doing a very good job explaining basically what the ternary operator is doing, okay? Because it's basically if, then, else, okay? So the condition we're evaluating is x is greater than or equal to 0. So that is not really just saying that x is positive, it is saying that x is non-negative, okay? So just a very slight correction to what Aaron said. I know it's nitpicking, but it is actually an important kind of nitpicking, because whether 0 belongs to this side or this side makes a difference, okay? So in this case, 0 belongs to the 2x side and not the -2x minus 1 side. Okay, so now that we know the mechanism, okay, it is probably helpful to look at a few examples, right? So we plug in values into this f, and then we try to go like, okay, so what is the result of that? Okay, so what I'll do is I'm switching to the whiteboard side, but what you guys can do is to stay on the notes, okay, using your own browser, and then keep an eye on, the live stream. So this way you can look at the result of applying f, and also look at the definition f at the same time, okay? So now I'm gonna go over here, and obviously it's still waiting me to hit the reset key, the escape key. So I'm gonna do it one more time in order for the settings to come into effect. All right, so let's go ahead and check out f of, okay, let's make it super easy to begin with. What is f of 0 according to the definition that you just saw? 0 is
0.
Exactly, okay, f of 0 is just 0. Okay, cool. What about f of 1? 1 is
2.
Sorry?
2.
2, yep. F of 1 is 2, indeed. What about f of -1? So now you have to be a little bit careful, because
-3.
No. If it were -3, then we have a problem with the codomain, because our codomain is the set of all natural numbers. So f of -1 would go to the negative side, so it's -2x minus 1, right?
So
it's 1. It's just 1, right? Okay, let me just kind of explain it, because it is -2 times x, and then the whole thing minus 1. Is that okay? So -2 times -1 is 2, and then 2 minus 1 is 1. So are we good? Are we okay with this?
Yep.
Okay, excellent. So let's see if anyone wants to guess what 2 is going to be mapped to. That's a pretty easy one.
4.
4, yep. And we'll do one more on the negative side, which is f of -2. So f of -2 is
3.
-2. Yep, exactly. Okay. So I just want to write the entire thing, and it is indeed 3. So do you guys notice a pattern here?
This is sort of how we count numbers with bits.
No, that's not true, because what is f of 3? Because if you're thinking about how we count bits, then f of 3 would be 8, but it's not. So f of 3 is, what is f of 3?
F of 3 in bits or in this equation?
In this equation.
Oh, in this equation, it would be 5.
No. It's because 3 is greater than or equal to 0, so we want 2 times x, and that's 6, right? There we go. Okay. Okay, let's do just one more, okay? Because I think we need to be able to see the pattern, and that's why we're doing one more. Okay, so, okay, and what would that be?
That would be 5.
That would be 5. Very good. Okay, so are we seeing a pattern here? How are the negative integers mapped, and how are the positive integers mapped onto the natural numbers? So Yalis is already ahead of us. Okay, very good. So that is correct. Okay, f of negative z would map to odd numbers, and I'm assuming negative z is referring to a negative integer. So all the negative integers would map to positive odd numbers, and all the non-negative integers would map to even numbers. And that is actually what it does. Okay, so very good observation, Yalis. If I mispronounce your name, just let me know, or put your pronunciation in parentheses, so I would try my best to pronounce it correctly. Okay, so that is exactly what it does. Okay, so this is one kind of funky way to, I would call this folding. Okay, so if you just kind of imagine, okay, let me take a look at myself in the video, because I want to see if I can actually record the motion of what I want to demonstrate. It's very unusual that I want to use gesture to represent something. Okay, so I'm going to step back here. Okay, so let's see. There we go. Okay, so this side are the negative integers. This side are the positive integers, and where my two hands cross, that's 0. Okay, so one set, which is the set of all integers, are both. It extends to infinity on both sides, and the set of all natural numbers only extend to one side. Okay, starting with 0. So it would seem that one set is bigger than the other one because one has both sides and the other one only has one side. What this function does is to basically interleave. So for every value that is a non-negative integer, it would go to certain natural numbers, and then for the negative integers on the other side, it would kind of fold it this way. Okay, this is hard to do because I cannot twist my hand into this, but I can kind of rotate it like this. So this way, we have the non-negative integers, and then we have the negative integers interleaved like that, and now they are both on the axis of natural numbers. So am I kind of explaining this okay or not?
It makes sense.
It makes sense. Okay, so but this is an interesting function. It has other interesting properties. Okay, so if I tell you, okay, on here, okay, if you know that, okay, I'm just gonna say f of some x, okay, is 67. Okay, can we figure out what x is? Okay, what do you guys think? Assuming f is defined the way that we define it in the notes, can we reverse the process? If you know the result of f of x is 67, can you be
Negative 34?
Negative 34. That is, I'm just double checking. That is correct. Okay. Yeah. All right. So Aaron is correct. So f of 34 No, negative 34, right? So f of negative 34 is negative 2 times negative 34, then the whole thing minus 1. So it is negative 60, nope, positive 68 minus 1, which is 67. Okay. Woohoo! Okay, this is good. And we'll do one more example. Okay, if you know that f of x is, let's try 32. Okay, can we figure out what x is? Okay, I forgot to open $sign, and that's why the equation doesn't quite look correct. All right. So Yales has got it correct already in the text channel. It is just 16, okay? So I'm just going to put it here and say f of 16 is 2 times 16, and that is exactly 32. Cool. Oh, okay. So it looks like, okay? I'm going to emphasize, the phrase looks like. So it looks like f is reversible. Okay, it just looks like it. Okay, if you give me the result of if you give me the result of f of something, I can reverse the process and find out what that value is. Okay, but can we find it? Can we actually find the inverse function of this f? Now, if you're reading the notes, it is already in there, but let's see if we can figure it out, just by reasoning out. Okay. So how do we find the inverse function of f? Okay, so that's our question now. So how do we reason this out and find it? So it sounds to me that you guys are convinced that negative integers get mapped to odd numbers, and then non-negative integers get mapped to even numbers. Is that correct? I think that's our observation.
Yes.
And that can be proven, using the original definition as well. Okay. So that means if we want to reverse the process, the first thing we want to know is whether the value is odd or even. Okay, so that seems to make sense. So we'll get started with that. Okay, so we'll say f inverse of some value, okay, we'll call that y, is based on whether y is odd or not. Okay, so how do we determine whether y is odd or not? Because the first thing we need to do is to find out whether y is odd or not, and we kind of have a pretty good idea that this is going to look like a ternary operator, because depending on whether y is odd or not, what I want to do next can be different. So now we just want to say, how do we know whether y is odd? So what operator do you need to use to differentiate whether a number is odd or not? There's two ways to do it. I just want one of them, huh?
Modulus 2.
Modulus 2. Okay, very good. So y mod 2 is a good beginning point, a good starting point. And then what do we do? Omar is typing, okay, and the rest is correct too. Aha, okay, so we can compare the result of y mod 2, and you can compare it to 0, you can compare it to 1. All it does is to kind of flip the true and the false side, because we know that y mod 2 has to be either a 0 or a 1, because y is a natural number. So whether you want to compare y mod 2 to 0 or 1, only changes, what we specify in the true side and on the false side of the ternary expression. Okay, so we'll just kind of go ahead and stay with this one. So when this expression is true, that means y is even. So when y is even, what do we do to reverse the value back to the integer that map to this particular value of y? Okay, divided by 2. Very good. Okay, so Yales is correct. We just have to divide it by 2. Okay, so let's go ahead and specify that. Okay. So we are dividing y by 2. Okay. What about the other one? What if y mod 2 does not equal to 0, meaning that y is an odd number? So for that, we already got a pretty good idea of what to do up here. So we just have to formalize it down here. Yep, so Yalis has got that one too. So we have a division by 2 again. But before we divide, we have to, okay, there are 2 ways to do it. We can say division by -2. Then we just have to specify y, is it +1? Yep, y +1 divided by -2. So does that make sense? Because that's exactly what we did over here. Okay, you know, we when we reversed the process, not this one. Let's see, where was it? I thought, oh, this is just the verification. I never really showed the actual math of how to reverse it, but this is the process. Okay, you add 1 to y first, okay, and then you divide it by -2. Then it gets mapped back to whatever integer that is mapped to this particular odd number. All right, so what we'll do is we want to double check, okay? So we want to at least verify that this f inverse is working with at least one of these values. So let's try out 5, okay? So we want to try out the f inverse of 5. Okay, so now we look at this and we go, 5 is an odd number, so we have to go for the else case. So when we go for the else case, then we end up with 5 plus 1 as our numerator, -2 as our denominator, and then that equals to 6 divided by -2. Okay, so let me just go really step by step. So we have 6 divided by -2, which is 3, -3. So now we go back to look at this and go like, yep, that is true. F of -3 is 5, and f inverse of 5 is -3. Cool. So why is this so cool that, you know, f inverse exists? What does it say about f? So this is going back to the discussion of injection, surjection, and bijection. So if I know that f has an inverse, what can I confirm out of those properties about f? It is 1 to 1, okay? It's a bijection. Okay, so Yalis and Joshua are both correct. Okay, it is a 1 to, it's a bijection. Okay, so f is a bijection. In other words, it is a bijective function. So what is cool about this is the definition of cardinality equivalency when we are talking about 2 different sets and each one has an infinite number of elements. Okay, so this is how we define Aleph Null. Okay, this is the actual formal definition of Aleph Null. Okay, so I'll just write it here. We'll say given X is a set. Okay, if there is a bijection, and the bijection is, okay, I have to move this to the side a little bit here. So we have a bijection f, and f is going to take X as the domain, and it maps it to the codomain of all the natural numbers. Then we say that X has a cardinality of Aleph Null. Okay. All right, so let's go ahead and take a look at this particular statement here, and I just want to make sure that everybody is understanding this particular statement. If you give me a particular set, we call x, okay, but x can be the set of all integers, it can be a two-dimensional space of integers and blah blah blah, okay. But if you give me a particular set, okay, we call x here, and we can find a bijection f, and you can map natural numbers to x or otherwise, because when we're talking about a bijection, it means it's reversible, but I'll just kind of choose to name it this way. So if you can find me a bijection so that the domain is x and the codomain is n, the set of all natural numbers, then we can claim that the cardinality of x, which is the set that you just gave me, equals to Aleph Null. So that is the definition of what Aleph Null is about. It's basically just asking, if you give me this kind of weird set that is not the set of all natural numbers, but if I can find a bijection, which means it is a one-to-one correspondence between elements of the strange given set and the set of all natural numbers, then we can claim that the strange set that you just gave me has the same cardinality as the set of all natural numbers. So do we have any questions about the definition of Aleph Null? How do we determine that a particular set has a cardinality of Aleph Null? Okay, I'm not seeing any questions or hearing any questions. Do you guys need more time, or we're good?
I'm good.
All right, cool, thank you. All right, so assuming that we're good, okay, thank you, on the text channel as well. So assuming that we are good, let's go ahead and look at something, some of the kind of weird items. Okay, this is back in the notes as well. So if you're reading the notes, you're good. Okay, so let's look at something like this. Okay, so I'm gonna type on the whiteboard, and I'll type, what if this x is the Cartesian product of natural number and natural number? Okay, well, if I ask someone who has not read this module before, and I ask, do you think the set of all coordinates on an infinitely large screen, okay, because it's two-dimensional, do you think it has the same cardinality as the set of all natural numbers, which is kind of like a single row of pixels that goes on forever and ever? Most people would say, no, I don't think so, because one is a two-dimensional kind of thing and the other one is a one-dimensional kind of thing. Okay, so most people would just kind of intuitively say no. And Yalis is saying yes, because I'm guessing Yalis has read the note.
Well, if they're both infinite in either direction, so if the 2D one is infinite in all directions and the 1D one is infinite both forward and behind.
In one dimension.
In one dimension, then they both equal to infinity, would it not? So
no, but it's not just infinity, because you have to find that bijection in order for the equivalency to be established.
Oh.
You cannot just say that they're both infinite and therefore they have the same cardinality. That is not what Aleph Null is about. Aleph Null is about the existence of at least one bijection between the set that you're interested in and the set of all natural numbers.
Okay.
Oh, okay. Well, that's that's interesting. Yalis has just finished a math major last semester. Okay, so that kind of that kind of explains a few things. Very good. Okay. Okay, that's actually interesting. It's good. When I was a graduate student, a computer science graduate student, I also had to take a few undergraduate math classes, and one of those was abstract algebra. And abstract algebra is the divide in the math curriculum. In other words, basically half the class did not make it in abstract calculus. And basically, it's the divide, okay? It just goes like, well, this is, the concept that, people have to understand if they want to be a math major. and basically have the class, well, I wouldn't say they're not smart. Okay, it has nothing to do with smart or not. It has to do with whether because of a lot of different factors, whether people can work with those concepts or not. So really has nothing to do with intelligence. It has more to do with how the brain is wired and understand abstract concepts. Okay. Yep, I was actually doing that too. I was almost dual majoring because math and computer science overlap a lot. I think they only differ by maybe 3 or 4 classes. So it was basically like getting 2 degrees for free for the price of 1. But if you guys try here with the CSU or UC, it is probably either impossible, they won't let you do it, or it will be frowned upon. And the reason why it is frowned upon, or it is not even possible, they won't let you do it, has to do with funding, because the school doesn't get a lot of extra funding when people want to double major. So universities want to push people out as quickly as possible, and people who double major usually need at least 1 more semester or a quarter to get everything done. So it is greatly frowned upon. You might be able to minor in math, and that's okay, but if you try to double major, a lot of times the university may not let you do it. Yep. All right, cool. All right, so now let's focus on this one here. Okay, how do we map a 2-dimensional space? So if you can just kind of imagine, one is a number line, it just goes like, okay, here's 0, here's 1, 2, 3, 4, and it goes all the way, to my right-hand side. And the other one is a 2-dimensional space, right? So you have, the x-axis going this way, and then you have the y-axis going this way. And each axis goes on forever and ever. So now you're spanning a 2-dimensional space. How can a 2-dimensional space actually maps to a 1-dimensional linear line that only starts from 0? Okay, it doesn't even extend on both sides of 0. Okay, it only goes on from one side of 0. So in order to explain that, I didn't quite set it up to do it this way today, but I can use a spreadsheet. Okay, so a spreadsheet is really helpful to do something like this, because a spreadsheet is nothing more than a big gigantic table where the cells can be calculated. Okay, so I can use a spreadsheet to do this, and I'm working on something offline here to get it started. But once it's started, I'll move it into your view. There we go. All right. So here's a spreadsheet, and we'll basically use the column number as our x-axis, and then we'll use our row number as our y-axis. But we'll use both starting from 0. Okay. So in other words, this one is known as coordinate 0, 0 in a 2-dimensional space. And this one here is, okay, I guess I don't need the quote, because if it starts with an open parenthesis, it's not considered a number. So this one is going to be a 1, 0, and this one is going to be 2, 0, and I'll work it up to like 3, 0, okay, because I think you guys got the idea. So this one here is going to be 0, 1, and the next one is going to be 0, 2, and the next one is going to be 0, 3, and so on. In other words, I'm just naming the cells based on their coordinates in a 2-dimensional space. Do we have any questions about this? No, Aaron. Just getting back to the text channel. We cannot use the inverse of the previous function because this needs a new function to begin with. So we're going to need a new inverse function. The other function doesn't work because the other function is still mapping a single dimensional space to a single dimensional space. The set of all integers is a linear space, it's a single dimensional space, but what we are looking at here is a 2-dimensional space. Each cell has quote unquote 2 specific values. Okay. So this particular cell is going to be 1 1, and this is 2 1. This one is 1 2, and this one is 2 2, and so on. Okay. So are we doing okay? So okay at this point, just basically in terms of how we number the cells based on their two-dimensional coordinates. Going from left to right changes the first number in the two tuple. Changing vertically from top to bottom changes the second number in the two tuple in each cell. So are we good so far? Okay, we're good. All right, excellent. So now we're going to say, let's start to assign natural numbers to these things. Okay, so we'll start with this corner over here, and we'll just say that, yeah, let's label this one as 0, and then we'll label this one as 1, and then we go diagonally. We'll label this one as 2, then we go back to here and label this one as 3, label this one as 4, label this one as 5. I think most of you got the idea, right? We just go diagonal, and now we start a new diagonal line starting from here. This is going to be what, 6, and this one is going to be 7, and this is going to be 8, this is going to be 9, and so on. So are we kind of understanding the approach of filling each cell with a single number that is next to the two-dimensional coordinate? We just basically go diagonal. Okay, we just sweep diagonally. So once we are done with this particular cell, we move on to this one, then to this one, then to this one, then to this one, then to this one. Then we start a new diagonal line from here. Then we go just sweep diagonally like this. Okay, so are we kind of getting an idea of how we fill each cell with both the two-dimensional coordinate, which is the two tuple in parentheses, and also the single number that is outside of the parentheses, So are we getting a general idea of how we number these things? Okay, so Yalis is saying yes, but I cannot rely on that yes to represent the whole class anymore, now that we know Yalis is double majoring in computer science and math. All right, what about the rest of the class? Do you need more time, or is this good? Okay, John says we're good. Okay, it's just a number pad, exactly. Okay, it is a number pad. But now the question is, okay, without expressing how we got the single value out of the two-dimensional coordinate, does it look like that this is a bijection? If I give you a two-dimensional coordinate, can you tell me what number goes there? Okay, if I just go pick this particular cell over here, okay, and I give you an infinite amount of time, can you figure out what natural number go into this particular cell? What do you think? Okay, so what I'll do, at this point is I'm going to make this process a little bit easier on myself. So I'm going to use some spreadsheet functions to figure out what should go into a particular cell. It may or may not work because this is in LibreOffice. It is not in Google Sheet. So maybe I should start a Google Sheet to do it, because I know the functions in Google Sheet much better compared to LibreOffice. Okay, so we can do that, and I have to navigate back to the share folder for this class. So just give me a second to do that. Oh, okay. All right. So I will share the spreadsheet, once I'm done with this. Okay. So let me just go ahead and create a new sheet. All right, so this is the sheet, and I just want a way to automatically create the two-dimensional coordinate of each cell. So the way to do that is concatenate. Okay, this is a string function, so it can supply a whole bunch of strings, and all it does is to say, okay, we'll just go ahead and merge all the strings into one. Okay, so we know that we have to start, whoops, okay, I can't type. Okay, so we know we have to start with the open paren, and we know we have to close with a closed paren. So it is what is in between that is kind of interesting. So the first one is our column number. So we use text to convert a numerical value into the text value into a string. It is not strictly needed, but it's probably a good idea to do that. So it is going to be just the column number of whatever cell we are in. So we just use column without any parameter, and that limits it to the current cell or whatever cell this formula belongs to. So that would give us, so I just want to give it a try. Oh, let's see, what am I missing? Oh, I forgot a comma. There we go. Okay. No. Okay, wrong number of arguments. Expects 2. Okay, I see. Okay, when I use text, I was assuming that it would take a default of just any number, but it doesn't like it that way, so I have to give it a format. Okay, there we go. And it is starting with 1, and that's because in a spreadsheet, the first column is column 1 instead of column 0. So that's easy to fix. We just have to subtract 1 from it. And now we have, the text representation of just the x-axis, just the x-coordinate. The y-coordinate is actually pretty easy to work with now that we know how to work with the x-coordinate. So the y-coordinate, which is separated by a comma first, is the text of the row number, and we have the -1 also because row 1 will actually return the value of 1, but we want a 0. And text requires a format string, which is just 0 itself. And there we go. All right, so let's see whether this works or not. So we fill in a whole bunch of stuff horizontally and vertically. Woohoo! All right. Is that okay? The reason why I'm doing this is not to teach how to use a spreadsheet, but I want to fill these in with actual values at some point. So I want to be able to do this, so I can fill in, a large number of cells without having to hand calculate a whole bunch of stuff. Okay, so that's the reason. So now I can now say, oh, okay, if we can do this, maybe we can also modify the formula of each cell so that we can also include the calculation of the value associated with a particular cell. In other words, for cell 0, 0, we want to somehow be able to mechanically calculate 0. For cell 1, 1, okay, we want to be able to automatically use a formula and calculate the value is 4, okay? But without such a formula, okay, and I ask you about, okay, what integer should go here? Okay, what natural number should go here? I think most of you will say, well, that's going to be tedious, but if we need to do it, we can figure it out. Because all you need to do is to start with this cell and say, this is 0, this is 1, this is 2, this is 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and so on until you get to the cell that I want you to give me a number for. Okay? In other words, it's tedious, but it's doable. Okay? In fact, if I give you an infinite amount of time, okay, I can just point to a really, really far away place, like here, and then ask, what natural number should go here? You just go like, well, it's going to take a while, but eventually I can tell you the answer. Okay, so that kind of tells me that this is a function. Okay, to calculate the value of one particular cell is really just a function. So the next question is, what is that function going to look like? So that is where I need to go back to my notes, because there's a lot of detail and I don't want to memorize or rederive all the details. So when we get back to the notes, okay, where we are at this point is here, okay. This is g of 0, 0 is 0, g of 1, 0 is 1, g of 0, 1 is 2, and so on. So this is really just a not so intuitive way to look at the way we number the cells in the spreadsheet a little bit earlier. So the bottom line is we want a closed formula, okay? We want an expression so that we can express this function g, so that we don't have to kind of really manually go through every diagonal line in order to get to the cell that we want. So Aaron is typing something. No. Okay, so that is a coordinate, okay? 2x comma 2y plus 1 is a coordinate. Okay. All right. So how do we get to that formula? So the rest of this actually is giving you an idea of okay, so I'm just going to show you a little bit at a time because I want to explain the reasoning. So what I'm doing here is this is not quote unquote a core concept in CISP440. It is not in the curriculum, you know, of this class. So what I'm explaining here is how do you solve a problem? Okay, it's problem solving when you can see a pattern. How do you convert what you can see as a pattern into a closed expression so that you can just go like, oh, it is really just this equation that can do it, okay? All right, so let me go back to the spreadsheet first, okay? So let me go back to the spreadsheet that is here, okay? And I'm going to make it more compact, so it's actually easier to see at this point. You know, it's easier for me to draw diagonal lines. So you can see that, you know, the value of this particular cell is a 0. This one is 1. This is 2. Okay, this is going to be 3, and this is going to be 3 plus 3, and then this one's going to be the previous number, the number of this particular cell plus 4. Why do I know? Because I can count the number of cells in this particular diagonal line. Because this diagonal line starting from this has 1, 2, 3, 4 cells. So when I want to compare the value of this particular cell versus the value of this particular cell, we know that they're off by 4. And using the same reason, we know that, you know, the value of this particular cell is the value of this cell plus 5, and then plus 6, and so on. Does that make sense? Because each diagonal line, when I move the base of the diagonal line from left to right, each diagonal line has one additional item as we move in that direction. Okay, so I'm not seeing any confirmation or seeing any question. So what I'll do is I'm going to color code things a little bit. Okay, so let me just use color coding. Okay, so this one I use yellow. This diagonal line I have to use we'll call it light blue or light green. Oops, not that one. This one over here. This one I'll call it purple. Okay, 1, 2, 3, 4 this time. And we can use that, and so on. Okay, so what I'm doing right now is I'm basically using color coding so that we can focus on the quote-unquote diagonal lines. Okay, so the next diagonal line, which is this one, has 5 things in it. So can everybody see that each diagonal line just has one more item than the one that is to its left? Okay, Very good. All right, cool. So let me just label this one, and then we'll move on. Okay. All right. So knowing that, okay, then we know if I can figure out the value of this particular cell, then I can just add 5, and that becomes the value of this particular cell. If I can know the cell, the value of this cell, the next one is just the value of this cell plus 6, and then plus 7, plus 8, and so on. Does that make sense? Because we are looking at the starting point of each diagonal line, and because each previous diagonal line has the number of elements in each diagonal line is just a sequence of natural numbers, so it becomes really just a summation of progressing linear natural numbers. Okay. So in the notes, that observation is also made. So in general, based on that observation, this is my conclusion. Okay, the conclusion is if we just focus on the first row of the two-dimensional space, okay, we just focus on one single row, then G of the value of cell x0 is basically the summation of 0 plus 1 plus 2 plus 3 plus 4 all the way up to and including x. That's my first observation. Well, let's see if that makes sense. Okay. So if we are, let's see, let's go back to the spreadsheet. There you go. So if we are looking at this particular cell, all I'm saying is the value of 40 is supposed to be 0 plus 1 plus 2 plus 3 plus 4. So that turns out to be what? 1 plus 2 plus 3 plus 4 is 10. So the question is, well, I mean, is it 10? Okay, let's count. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, it is indeed 10. No, it's not 11. It should be 10. You probably counted from 1 instead of 0 at the beginning. Okay, so, okay, this method seems to work. Okay, now we go back to this form, okay, this particular expression, and go like, well, this gives us a pattern. Okay, if I were to do this with a loop, I can easily do this, right? Because all we need is a for loop so that we can go through all the values and then add them up. But that's not a very fast way to do it. Okay, if I can just use a closed form, which means squares and divisions and multiplications and additions and subtractions that does not depend on x. Okay, I shouldn't say that. So that the number of items in the expression does not depend on x, that would be great. So that means I'm looking for a closed form of summation up to and including x starting from 0. Is that okay? Does everybody understand my intention? I look at this and go like, yeah, this is a fairly good generalization. But if I say, what is G of 216, 0, wow, that means I have to add, all the way from, if you say, okay, you don't have to add 0, fine, but you have to add from 1 to all the way to 200 and whatever number I mentioned. That takes a while. Okay, so the question is, can we do it faster? And Yales has the answer, but what I'm interested in is not the answer. Okay, not to mention, this is not to downplay the contribution of Yales, but what I'm saying is the important part is not the answer. It is how we get to the answer. Okay, I mean, you can look it up. I mean, this is a fairly common summation thing, and you can find it on the internet. But the question is, if it is up to you to derive it, how would you derive it? Okay, so this is how I do it. Okay. So I just expand it and go like, okay, 0 plus 1 plus 2 plus 3, blah, 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 all the way up to x is really a horrible way to say something like that. It is much better to use the sigma notation. The sigma notation is the summation notation. So basically it is a loop. where I is the index variable. It goes from 0 up to n including x. And then the value of this thing here is added, for each iteration to get to the sum. Are we doing okay so far with the sigma notation? Is everybody familiar with the sigma notation?
Yes.
Okay, excellent. All right, so then the next stage is to look at this. Okay, very good. Thank you, Omar and John and Aaron. So the next stage is to say, well, Tech, hold on a second here. Because if x is an odd number, then we end up with an even number of items because we started with 0. And if x is odd, when x is even, then we end up with an odd number of items. So they're kind of two different cases. Well, I go like, fine, let's think about it as two different cases. So I use a ternary expression again. So this time I say, well, let's look at x mod 2 again. And if x mod 2 is not a 0, which means x is an odd number, then we use this particular, okay, I'm not doing a very good job selecting. Then we use this portion of the expression. If x mod 2 is indeed a 0, then we're going to use this particular expression over here. So the only difference between these two is this one handles the case when we have a even number of terms. This one handles the case when we have an odd number of terms. So that one extra item that is in the middle of the entire series is x divided by 2. So this is the first part of the summation. This is the second part, or the last part of the summation. This is the middle part. When we have an even number of terms, then we can evenly divide it so that we can say this is 1/2 of it, and this is just the other half of it. So this whole thing just has to do with how we play with the start and the end of the indexes for each sigma. So I'm going to leave it up to you guys to read this part, but I will explain, what goes on between the rows, okay, between these lines. So coming from here to here, okay, I'm folding these two into one single sigma notation. So I'm looking at by changing the indexes. In other words, if I want a sum where I starts from x minus 1 divided by 2 plus 1 all the way to x, and each term that I'm summing up is just I could have just changed the index I to go from 0 to x minus 1 divided by 2, but then each term that I'm summing is not I anymore, it's going to be I minus 1. So that's how I combine these two sigma notation into one single one, and this is the term that is inside of it. Okay. On the other side, it's the same thing. Okay, I'm just playing with by changing the start index and also the start value of the index I and the end value of the index I of the second sigma. By changing and moving that around, I can end up changing the expression I so that the expression I becomes x minus 1, but then I can unify the start index and the end index of both of the sigmas, so I can combine the two sigmas into one single sigma, and then each term of the individual sigma is just added to the other term of the other sigma. So that's the trick that I did between these two lines. So what do I do with the third line? Okay, this one takes a little bit of mental acrobat to get it done, mostly because you kind of have to, the best way to do it is to give yourself examples. Okay, so give yourself an example and use a specific x. So in this one, let's say x equals to 5. Okay, nope, I take it back because x is, nope, it's right. So x is 5, is a good example to look at what numbers you're actually adding here. Then you can actually see how we can combine the two sigmas into one. Because if you don't use a concrete number, it takes a little bit more juice to figure it out. But once you fix x to be 5 in this case, and then maybe x equal to 6 in this case, then it's easy to actually see, oh, okay, so that's how we are just playing with the sigma to come to the second line. Okay, So between the second, between this equal to and this equal to over here, between these two lines, is actually very easy, because each term we are summing is I plus x minus 1. You go like, wait, hold on a second here. This I is canceled by this negative minus I, so we really just get x back over here. The same trick is done on the other side. When you look at this I and this minus I, they cancel out. We just get x back, okay? But when you get x back, okay, and we just have an expression of x in each iteration of the loop, nothing depends on I anymore, right? So if nothing depends on I, then we are really just saying, in this case, in this particular case, we are really just saying, let's add x how many times? X minus 1 divided by 2 plus 1 times, okay? So this plus 1 over here is necessary because we started counting from 0. So if you count the number of iterations, it is not x minus 1 divided by 2, it is x minus 1 divided by 2 plus 1. And then for each iteration, we are adding x to the running sum, okay? And we're basically doing the same thing on the other side, except on the other side, because x is an even number on the other side. So we basically, when you need to count how many times we go through the loop, it is exactly x divided by 2 number of times that we go through the loop. So this entire sigma, okay, is simplified to this term over here. The x divided by 2 outside of the sigma is still outside of the sigma, so that's a separate term in this case. Okay, now between this and this, okay, that's just a simplification. So instead of having a plus 1 that is outside of the fraction notation, I just move that plus 1 into here and say, and just add 2 to the numerator, and we get rid of the plus 1 on the outside of the fraction. So that's kind of like a simplification. And then on this side, I mean, that's really, I just took out some of the parentheses on the other side. And then from here to here, okay, I just move, I did two things. Minus 1 plus 2 is just plus 1. And then I just move this multiplication by x to the numerator of the fraction. And I mean that's really just kind of moving things around a little bit. And then on the other side, I factor out the x divided by 2. So the x divided by 2 is on the outside. And then I have x plus 1, as the term to multiply to x divided by 2. So at this point, okay, when we get to this part here, okay, let me select just the part that I want you to look at. It's not as easy as it doesn't quite let me do it that way. Okay, so when we are looking at this part here, you can see that they really are the same, right? Because all we have to do is to move x plus 1 as a term that is multiplied to x divided by 2 onto the numerator of the fraction. Now we end up with, hey, tech, this is really kind of weird, because no matter what x is, whether x is odd or not, okay, we ended up with this closed form, which is x times x plus 1, the whole thing divided by 2. So that means it doesn't depend on whether x is odd or not. We just end up with x times x plus 1, the whole thing divided by 2. End of proof. Okay, so Yales is correct all the way back at 1140, which is 10 minutes ago. So in other words, some people can look at this and go like, hold on a second here. Tech, you just wasted 10 minutes to explain something that someone just mentioned earlier. The answer is, well, if you look at it from the perspective of what can we do to simplify a summation like this, then the answer is yes. Okay, we had the answer 10 minutes ago. But I think it is important for me to explain how a person can derive it. Okay, and this derivation is my own. Okay, I did not copy it from Wikipedia. I did not look at somebody else's proof. I just go like, well, I know, from looking up on the internet, I know this summation ends up, being something like this. but I want to be able to prove it, okay? Because I don't want to take the conclusion from somebody else and just say, okay, because somebody already came up with this conclusion, I don't have to do it. But that's a tech thing, okay? I'm not expecting everybody to think in that particular way, but by illustrating how I came up, with this proof, I'm hoping that some of you would also, let me see, I'm trying to come up with the right word here. So I'm hoping some of you would also take this approach when you take a class, is not to take something for granted because it is done already. Particularly at your stage, because you're learning, you're a student, I think it is important for you to try to do these proofs yourself, because the more you perform these proofs, the more you are capable of problem solving. In other words, in this case, the answer is here already, okay? Why would I want to spend the time to do all of this? It's the same kind of deal as looking at someone who's jogging, okay? And you ask that person, why are you jogging? Where are you jogging to? And where's your destination? That person will say, well, I came from home and I'm gonna jog a circle around the block or several rounds around the block, and then I'm gonna go home and and rest. And you go like, what is the whole point? Right? What is the whole point of jogging? This is jogging, okay? So what is the whole point of jogging? I want you guys to answer that question, especially those of you who are health conscious and actually go to the gym and work out. Why do you lift that dumbbell only to put it back down and then go home? You're not even taking the dumbbell home. Why are you working out? That doesn't seem to make sense. Exactly. Okay, so Yales and Omar, they're all correct. Okay, this is an exercise. Okay, it keeps your muscle in good shape. Okay, not just your muscles, right? Your heart muscle, your lung, everything is in good shape when you do this exercise. It's the same thing. Okay, working out proofs like this is like jogging for your mind. Okay, the mind is the health of the mind is very easy to ignore. Okay, if you're a couch potato, okay, eventually someone is going to tell you and let you know that Tag, you seem a little bit heavier than 2 months ago, and you don't seem to have a whole lot of energy, because it's obvious. Okay, it's physical, but the mind is not obvious, right? It is something that people cannot tell. Oh, okay, roll call. Thank you. Trying to remember which word I used. It has to do with Aleph Null. I'm just gonna cheat. I cannot remember. That is very typical of me. I'm a very good person to keep secrets because I really forget things quickly. Nope, that's the wrong class. All right, over here. Yep, we're down to here. Road taking. There we go. It was a word that's related to today's class, but I just cannot remember. When I typed it in, I was thinking to myself, yep, this is pretty obvious. Let's see. Okay, so you guys can see the answer on the screen. Fold. Of course. Because we are folding spaces, okay? So what I want you guys to do is, one, do the row taking activity right away, okay? So don't wait, just do it right away before you have lunch. And the second thing is, we do have a homework assignment over the long weekend, and it's due right before class on next Tuesday. So that one you kind of want to spend some time, okay? So don't submit, okay, unless you're 100% sure that you're not going to change your answers. And then number 3 is to review all the things that we have talked about up to this point. At least do that much, okay? And if it is possible, if you have time, read ahead of me. folding spaces, okay? Because we are folding a two-dimensional space into one. See this two-dimensional space? We're folding this space into a linear space of 0, 1, 2, 3, 4, and all the way up to the natural numbers. So we are folding space here. We're not folding physical space. I wish I could do that too. But we are folding a natural number space. Multi-dimensional natural number space folding into natural numbers. All right. So what should we read before next Tuesday? I would say that if you can finish reading this entire thing and actually understand how everything is derived, that would be good, okay? Because it's not long. It is not about the length or the number of words. It is about understanding the concepts, because this entire thing not only gives us the okay, let me just get to the right place here. It doesn't just give us okay, right here. So it doesn't really just give us the function in one direction, which is mapping, in this case, a two-dimensional natural number space to a one-dimensional natural number space, but it also works out the reverse, okay? The inverse function is derived over here. So if you can follow every single step and go like, okay, I see how this works, and I see how this works, and I see how this works, I think that would be a good achievement, you know, by next Tuesday. I have a strong suspicion that by next Tuesday, we might be able, just might, be able to get started with the next module, which is about relations. So if you finish the Aleph Null module and go like, yeah, I'm feeling pretty good about this, I seem to understand all of the concepts, then go ahead and just move on to relations. But it's not 100% necessary to move on to relations. But if you have time, okay, just kind of keep going forward. All right. All right, so we are running out of time, and I think I have been running out of time for 10 minutes already. So I know you guys want to get lunch. I'll be here for my office hour between noon and 1 o'clock. So if you have any questions, you'll just kind of pop in and I'll answer your questions, possibly with more questions, but I will address the question. So when I say answer, it is not the correct word. I will address your question. All right, so I think that's it for the lecture. Unless somebody has a question or comment that I should address before I stop the live stream, I'm gonna end the live stream now. Okay, I'm not seeing anything. All right, excellent. So I'm gonna end the live stream and the voice connection.